In this video, we're bringing a modern, eye-catching lighting effect into classic Java Swing, real-time, soft shadows that follow your mouse like a spotlight. We'll start from scratch in NetBeans, using a simple JFrame and a custom JPanel. In the Projects panel, right-click your package, choose New, then JFrame Form. When it appears in Design View, resize the JFrame to your preferred size. Go to the Properties window and change the title to Real-Time Shadow Casting. Next, from the Palette window, drag and drop a JPanel into your JFrame. Resize the panel so it completely fills the JFrame, edge to edge, matching the full window size. Go to the Properties window, find the Variable Name field, and set it to Panel Container. In the Projects panel, right-click your package, choose New, then Java Class. Name the class Shadow Panel. At the top of Shadow Panel, add our imports. Swing gives us Swing components like JPanel and JFrame. AWT give us core 2D drawing tools, colors, strokes, and the graphics 2D. API event give us mouse events so the light can follow the cursor. Geom give us geometry types like rectangles, paths, and points. Image give us image buffers and the blur operation for soft shadows. Util give us collections such as list and array list to store our shapes. By extending JPanel, we can override its Paint component method to draw our custom UI, shadows, and lighting effects directly onto it. Next, import Java List class. The list interface lets us store an ordered collection of objects. First, we create a list to store our shapes. This will hold all the rectangular UI elements that will cast shadows on the screen. Next, width and height of our drawing area, in pixels, the size of the panel we'll render into. These variables store the light's position, starting roughly in the center of the panel. They're floating point numbers, allowing smooth movement. These are two off-screen images. We'll first draw sharp shadows onto shadow layer, and then apply a blur to create soft edges, storing the result in blurred shadows. Finally, this is our blur operation. We'll configure it once in the constructor with a Gaussian-like kernel, and reuse it every frame for performance. Inside our Shadow Panel constructor, we start by setting the preferred size. This tells Swing we'd like our panel to be 900 by 600 pixels, matching the constants we defined earlier. Next, gives our panel a dark gray background, almost black, which helps the light and shadows stand out. And finally, set opaque ensures Swing will fully paint the background instead of letting anything behind the panel show through. Next, we add some sample shapes to our blocks list. This creates a rectangle positioned at x120, y120, with a width of 140 and a height of 80 pixels. Another rectangle, placed further right and slightly lower, with a larger size. This one is tall and narrow, positioned near the right side of the panel. a medium-sized rectangle lower down on the left. And finally, a wide, short rectangle near the bottom right area. These rectangles will act as our UI cards or objects in the scene, each one will cast a shadow based on the light's position. Now we create two off-screen images, also called buffers, where we'll draw our shadows before putting them on the screen. This will store the sharp, freshly drawn shadows in full color with transparency. The ARGB means alpha, red, green, and blue channels. This second image will hold the softened, blurred version of those shadows. By keeping them separate, we can blur the shadows without affecting our main UI drawings, and then composite them smoothly into the final scene. Next, we create an array of floating point numbers called W. These numbers are the weights for a 5x5 blur kernel. Think of it as a stencil that tells our program how much to blend each pixel with its neighbors. The values are largest in the center, with smaller numbers toward the edges. This creates a soft, Gaussian-like blur, perfect for smooth shadow edges. First, we need to normalize the blur weights so the overall brightness stays the same after blurring. We start with a sum of 0. We loop through each weight and add it to the sum. Then, this divides every weight by the total sum, so all the weights together equal 1. Finally, we create our blur operation. Here we build a 5x5 kernel using our normalized weights, and tell it not to alter pixels at the image edges. This blur object will be reused every frame to soften our shadows quickly and efficiently. Now we make our light follow the mouse. Mouse motion listener that reacts whenever the mouse is moved or dragged. Inside mouse moved and mouse dragged, we set light X and light Y to the mouse's current coordinates, so the light position instantly updates as you move the cursor. Next, swing timer that fires every 16 milliseconds, about 60 times per second. Each time it runs, it calls repaint method, which redraws the panel with updated shadows. Together, the mouse listener and timer give us smooth, real-time interaction and animation. Now we'll create drawLightGlow method with takes Graphics2D parameter. Integer R sets the glow radius to 120 pixels. Then we create a radial gradient paint object. The center is at the light's current position, with a smooth gradient that fades from a warm yellowish white at the center, to completely transparent at the edge. We save the current composite mode and composite old, switch to alpha composite so our glow draws over everything else, and set the paint to our gradient. Fill method draws a soft circular glow around the light. Finally, we restore the old composite mode so the rest of our drawing isn't affected. The result, a warm, subtle spotlight effect that makes our shadows pop. This method, Project Point, takes a corner point of a shape and projects it away from the light to create the shadow's far end. First, we calculate the vector from the light to the point. Then we measure its length. If the length is extremely small, meaning the point is almost on top of light, we force it to a tiny value to avoid division errors. Next, we normalize that vector by dividing by its length, giving us ux and uy, the unit direction away from the light. Finally, we return a new point, where d is the projection distance, making the shadow extend far beyond the object. This method, edge faces away, helps us decide if a particular edge of a shape should cast a shadow. First, we find the midpoint of the edge between points A and B. Then we calculate the vector from the light to this midpoint. Next, we determine the edge's direction. From that, we get the outward-facing normal of the edge by swapping the coordinates and flipping the sign on one. Finally, we take the dot product of the light vector and the edge normal. If this value is greater than 0, it means the light is hitting the front of the edge, so the opposite side is in shadow, and we return true. The render shadows method builds our shadow layer from scratch every frame. First, we grab a Graphics2D object from shadow layer, the off-screen image where shadows are drawn. We clear it completely using set composite method, followed by filling the whole area with transparency. Then we switch back to normal drawing mode with Alpha Composite Source Over and turn on anti-aliasing for smooth shadow edges. We set the paint color to a semi-transparent black. Using new color constructor method, this will be the color of our shadows. Now, for every rectangle in our blocks list, we first collect its 4 corner points into an array C. We then project each corner far away from the light, about 2000 pixels, using our project point method, storing these in array P. Next, for each edge of the rectangle, we check if it faces away from the light by calling edge faces away. If it does, we create a Path2D float quad that connects the edge to its projected edge, forming a long shadow polygon. We fill that polygon with our semi-transparent black color, adding it to the shadow layer. Once all shapes have their shadows drawn, we dispose of the Graphics 2D object to free resources. Finally, we pass shadow layer through our blur operation, storing the softened result in blurred shadows, ready to be drawn onto the screen in the main painting step. The Draw UI method is responsible for painting our background and the solid shapes that will cast shadows. First, we create a vertical gradient paint. This fades from a slightly lighter dark gray at the top to an even darker tone at the bottom, adding depth to the scene. We set that gradient as the current paint and fill the entire panel with it. Next, we loop through every rectangle in our blocks list. For each one, we first set the color to a medium dark gray, and fill the shape. Then we switch to a slightly lighter gray, set a stroke width of 2 pixels, and draw the outline. This combination of gradient background, solid fills, and borders gives our scene a clean, modern, card-like look, ready for the shadows to make it pop. This is our paint component method, the heart of all our drawing. We start by calling Super Paint Component method to clear the panel and paint its background color. Then we create a fresh Graphics2D object from the original graphics. This lets us safely apply custom settings without affecting anything else. We turn on anti-aliasing for smooth edges. Next, we draw the UI shapes, the rectangles or cards in our scene, by calling Draw UI method. After that, Render Shadows method builds the shadow layer, and we immediately draw the blurred version onto the screen. Then we add the light glow on top by calling Draw Light Glow method. Finally, we set a semi-transparent white color, choose a bold font, and display the current light coordinates in the top left corner for debugging. At the very end, we dispose of our Graphics2D object to free up system resources. Import the border layout class so our panel can fill the frame correctly. Now, inside our shadow window constructor, right after init components method, we set the layout of our panel container to a border layout. This makes it easy for any component we add to automatically resize with the window. Then we create a new instance of our shadow panel and add it to the center of the container. Finally, we call Pack method so the window adjusts its size to fit everything perfectly. And that's it, real-time, soft shadows in plain Java Swing. Try adding more shapes, colors, or even multiple lights. If you found this useful, hit like, subscribe, and keep coding creative.